So how do we know that there is a core and that the core is made up of a liquid outer core and a solid inner core? And the answer there comes from the same technique that we saw Mohorovičić use in 1909 to essentially see how the behavior, or when you measure the seismic waves, or whether you can even measure the seismic waves, the different distances from an earthquake. So if there's an earthquake right here, and we're calling that 0 degrees, let's remember a couple of things here. Let's remember that P waves can travel through anything. They can travel through solid or liquid or air for that matter. So they can travel through anything. But S waves can only, S for secondary, S waves can only, these are the transverse waves. These can only travel through solids. So it turns out that if an earthquake happens at 0 degrees and you have seismograph stations all over the world, and these are extremely sensitive in order to be able to measure earthquakes that are happening thousands of kilometers away, it turns out that there's something called an S shadow. An S wave shadow. You can measure, if these are S waves, you can measure them here. You can measure them here. They can go all the way over here. They can go over here. They can go over there. You can measure them over here. So you can measure them at all of these points. But then all of a sudden at 105 degrees, and so we're measuring 0 degrees here and we're going outwards like that. All of a sudden at 105 degrees and further, you stop measuring S waves. They don't get, for some reason, you would think that the S waves would get over here. They would get over here. Maybe they would be a little bit weaker, but they would be able to get all the way over here. But they just abruptly stop. No more S waves. So in this whole area right over here, you get no S waves. You get no S waves. And obviously, I could flip this picture over, and you would see a symmetric thing on the other side of the globe, that all of this area over here you also would not see. You would also not see S waves. You'd only see them from 105 degrees in this direction and 105 degrees in that direction. And the only reasonable explanation that we can give is that there must be some material that an S wave cannot travel through, that it would have to travel through to get to these points beyond 105 degrees. And we know that S waves only travel in solids. So the assumption there is that at some point beyond 105 degrees, it's hitting liquid. So that's what tells us that this right here is probably a liquid. It's hitting some layer that is liquid. So that tells us that there's a core, and at least the outer part of that core is liquid, enough to stop S waves. So the S waves, because it only travels in solids, it leads to this S wave shadow. And this tells us that we have a core. And that core, at least the outer part, is liquid. We don't know yet whether the inner part is liquid or solid. Now, the next point of evidence is, how do we know that there's an inner core? And we can use P waves for that. A P wave can travel through anything. But remember, as you get denser material, in general, for the same type of material, if you get denser material, it's going to move faster. So it's going to refract outwards like we've seen over here. But if it goes into a liquid, in general, sound waves, or I should say P waves, seismic waves, moves slower in liquids. And so the refraction patterns we get when we do measure from seismograph stations around the world is that it looks like the P waves they're kind of doing this, what you would expect in the mantle, but then they're getting refracted as if they're going into a slower medium as they go through the outer core. And we see that right over here. And then they get refracted again to get to some point on the other side. Now, that is just what you would expect if it was all liquid. But if you go to stations that are even further out, it looks like, if you just look at the refraction patterns, and you can now model this with fancy computers and get all the data points, but you could say, well, the only way that reality can fit the data that we get based on when things reach here is if the P waves are being first refracted through the outer core, but then they're refracted in a way that they're going through denser material, significantly denser material in the inner core, and then they're just continuing to refract the way you would expect. So it's really the refraction pattern of the P waves. And frankly, the fact that there's this, what you call a P wave shadow, The P wave shadow by itself, all that tells you is that kind of roughly crazy things are happening someplace in the core. But the real way to know that we have an inner core that's solid, as opposed to the whole thing being liquid, is that the P waves is the pattern of when and how the P waves reach essentially the other side of the globe. And then you can kind of, based on modeling how waves would travel through different densities and different types of mediums, you could say, well, there's got to be an inner core right over here. And obviously, it's a lot more math than I'm going into. But if you do the math based on the shadow and you know the speed of the material and all of that type of thing, then you can figure out the depth at which these transitions occur. We know that we have a transition from mantle to outer core here, and then a transition from outer core to core there. So hopefully that satiates your questions about how do we know what the composition of the Earth is without ever having without having to dig down there, because we've never even gotten below our crust.